All right. So, yep. As Chris was saying, I'm Tyler McMullen. You can find me on Twitter right here at TBMcMullen. If you disagree with the things that I say, you can feel free to yell at me. You can actually just yell at me regardless. I'm actually totally fine with that. And I do work for this company. I'm the CTO of Fastly. And yeah, if you like the things that I'm going to be describing here, this is interesting to you, you should feel free to come up and talk to me afterward. We are always looking for very skilled distributed systems people. Okay. Okay, what's up? I figured, it's the first day of QCon SF. We would start like nice and slow, have a gentle, high level, description of distributed systems. I'm just kidding. We're going to build an gnarly distributed system together. So this talk is kind of my response to what I see as like the two types of distributed systems talks, right? You either end up usually having talks about theory without implementation, which is still useful in its own right, or you have implementation without theory, where speakers are often describing like, oh, okay, we tied this technology to this technology and bam, distributed system, which is also useful if you're trying to figure out like the practicalities of things. But I rarely find one that actually tries to bridge the gap between those two. So this is my attempt to do that. So we're going to have plenty of theory, but we're also going to talk about some specific technologies. We're going to design a system that involves cluster membership, fault detection, rendezvous hashing, gossip, and CRDTs. And I have 45 minutes to do it, so we should probably get started. So let's talk about the project itself, right? Like, you can talk about all these things in theory or in practice, but like if you don't actually talk about something that is like real, it kind of loses a lot of meaning. So the project that we're going to talk about is kind of specific to Fastly, but a lot of the principles still apply to other things. So if you're not familiar with what Fastly does, we're essentially like a middleman. We're a proxy. This is one way of putting it anyway, right? We sit in between your users and your origin servers. And so we try to do things there at that middle layer that you couldn't necessarily do at any other individual place in the network, right? So really, in like the lowest possible terms, you take a request from an end user here on the left, and it sends it through to the origin server on the right. Easy enough. But rarely, of course, is it actually just one server on the right, right? Most of our customers have many servers, whole clusters of servers, data centers sometimes, right? And so really we're talking about a much larger number. And so really what we're talking about is like load balancing of some kind. So individual requests come from the user and may get routed to one or a different origin server. Easy enough, right? But here's where this project actually comes in. If you're doing load balancing, of course, you need some way of detecting when one of those servers is gone, is dead in some way or another. So we need some way of making sure that this doesn't happen. Man, I have a lot of animations in this talk. We, of course, want to be able to route around like individual failures in our customers' origin servers, right? So we need some idea of health checks. But the problem is actually a little gnarlier than that. We can't just health check everything. Because, of course, it's not just one data center that we're talking about. We have many data centers. Uh-oh. There we go. Right, so we have many data centers here. And the trick with this is that the idea of health and health checking in a distributed system like this really depends on your perspective within the network. So from each of these, from the perspective of each of the individual data centers, different origins may appear to be up or down, right? The route that you take through the internet has a great effect on the health, the appeared health, right? It's all about perspective and vantage point inside the network, right? Okay, so essentially, we're designing a system that does health checks, but it needs to operate on a per data center basis. So that actually makes it easier, right? Because that means that we're not having to share information between multiple different data centers. Great. Okay. But of course, it gets a little bit more complicated even. Each of these data centers isn't, of course, a single server. Each of these data centers actually has many servers in them, anywhere between 4 and 64, sometimes 128 servers in each of our data centers, right? And the trouble is, you of course can't do health checks from every single server. That's just called a DDoS. If we were health checking, let's say you had your health check set up at like once every second, and we were health checking from every one of our servers, that would mean you're getting thousands of requests per second, right? So instead, what we really want is to be able to assume that all the servers in one of our data centers actually have the same perspective in the network, right? And so what we really want to do is say, like, okay, only one of our servers within each data center should be doing health checks on your origins. Okay, now we have a distributed systems problem. Because, of course, sorry. One of the other troubles with this is that just due to like sheer asynchrony in the network and also like the design of our particular network, not every server in every data center has the same view of which origins exist or don't exist at any one time, right? Even just looking at the asynchrony of the network, if you deploy a new server, you say, hey, Fastly, I have this new server sitting here. We can't put a lock over the entire system and say, okay, we're going to hold on, everybody stop, we're going to like deploy a new server now, right? So like it'll arrive at different servers at different moments, right? And so for individual like minutes, seconds sometimes, different servers may have a different view of which origins exist and which do not. Okay, now it's even more complicated. Okay, so essentially what we're talking about here is we need a way to distribute work, right? We need a way to essentially decide on ownership. Which one of our servers, which one of our nodes is going to take ownership of doing health checks for each individual origin server? Again, ideally we'll only have one inside each data center doing this. So we need to distribute this work across them in order to share, and then we need to share the information that they're learning from doing these health checks with all the other servers in the data center. Is this making sense so far? Good? Okay, great. But of course, we also have to deal with server failures on our side, right? If an individual server inside one of our data centers fails, we need to make sure that the work that that server was doing is taken over by someone else. Okay, great. So what we're talking about here is 50 plus data centers spread around the world, anywhere between 4 and 64, sometimes more servers in each data center. Talking about thousands of servers then, and we're also talking about tens of thousands of origin servers that we're worrying about health checking. All right. So to recap, the system that we're going to design is something that keeps track of origin health per data center and makes sure that regardless of our server's failures, there is someone always doing health checks of your origin servers. Okay. System needs to handle server failures gracefully, needs to stay in sync as much as possible, or at the very least be deterministic when it does go out of sync. And ideally, again, only having one server health checking each origin server per data center. Okay. Everybody still with me? Cool. All right, so let's talk about one possible solution to this. We could use a system like etcd or Consul or Zookeeper. These are what you might describe as, I imagine most of the people in the room here have heard of the CAP theorem, right? CAP. This is the whole idea behind okay, if you have partitions in your network, which you do, you can only choose between consistency and availability, right? You can't have both. So essentially, in the case of Consul or etcd or Zookeeper, what we're talking about here is this idea of atomic broadcast. The idea is that it's a fully consistent system, and if there are, say, partitions that happen inside your data center, it means that that system may in fact stop, right? Which is great in some ways, right? Because it means that we can apply a total order to every event that happens in the system, which would be great. It would make this whole thing a lot easier. But my argument is that in this case, also because this would be a boring talk if I was just use Consul, in my opinion, this is actually too strong of consistency for this particular application. In other words, in the presence of partitions, we are going to attempt to choose availability, right? Consul chooses consistency. Our system is going to choose availability. So what we're essentially talking about in this case is some form of eventual consistency. Great. But really the thing that we care about, the thing that we actually care about here is this idea of forward progress. We want to make sure that regardless of what happens inside our network, inside our data centers, that each individual server there, regardless of whether or not it can talk to the other servers, we want to make sure that it can always make forward progress. Another way of looking at this is to say that in the case of a system or network failure of some kind, I would much prefer for us to do 2 health checks against your origin servers than to do 0 health checks. Does that make sense? So obviously, this is kind of the idea of like coordination avoidance, right? Obviously, we need to communicate, we need to coordinate in some way, but we want to make sure that that communication, that protocol that we design, can't block forward progress on any individual node. All right. A great paper on this particular thing is coordination avoidance in database systems by the venerable Peter Bayless and Joseph Hellerstein and so on. So the question is really if we can't just rub some Raft or Paxos on the problem, what can we do? What guarantees can we continue to make regardless of that? If we can't rely on ordering and atomicity to solve our problems, which is what linearizability, our CP type system would give you, we need to decide which invariants we need and which we don't. So, okay, let's talk about ownership. So, just to recap again, this is the idea that we need to spread work around and handle failures when it occurs. Okay, so how many people here have heard about rendezvous hashing? Wow, only a few. Neat. I'm happy to help. So rendezvous hashing was invented at the University of Michigan in 1996. It was actually invented concurrently with consistent hashing, which I imagine a lot more people in the room know about. It solves the same problem, but in a significantly different way, and is good in different circumstances. So what it basically just looks like is this. It's actually really straightforward. So H is just a hash function. Simple enough. Any hash function. Probably want to choose a good one. I don't know. S of n here is what we're talking about, is the set of live servers, the servers that we care about within a particular data center. The O in this case is the thing that we are hashing, right? So in this case, it's an origin server that we're deciding on the owner of. And what we get out of this is a weight or priority. So what this ends up looking like is that if I go and I pass an origin into this and I iterate through this hash function for every server in one of our data centers, what you end up with is an ordered list. You end up with a prioritized list of which server should own a particular origin. Does this make sense? Right. So yeah, that's the whole idea here, is that for any individual origin server, we want to have a prioritized list. So we know that if this server is up, if server A or B is up, that one is the one that should own it. If it's down, here's the next one in the list that should own it. Okay. So let's talk about failure detection then. All right. So if we're going to communicate in a cluster or move work around in the cluster, we need to know who is in the cluster, who is out of the cluster, who is alive and who is dead at any particular moment, right? Oh yeah, nice. So one of the ways that that people have started doing this lately, one of the more popular failure detectors is the SWIM failure detector. This has become one of the more popular ones over the last few years. And so I guess I'll just walk through roughly, very high level, how this works. So the idea here is that every so often, servers that are in a data center, they wake up and they say, okay, I know that this server used to be here, my peer used to be here, and so I'll wake up and I'll say, okay, hey, are you up? Right? And that server responds and is like, yeah, I'm up. Great. Okay, cool. Now we know that that server is up, and server 1 in this case would then broadcast that around the network and say, hey, 3 is still alive, everything is cool, keep moving. On the other hand, sometimes what happens is that server 1 will say, hey, you up? Server 3 doesn't respond and nothing happens. So the idea with SWIM is that SWIM then says, hey, 2 and 4, can you check on 3? Maybe there's just a little communication blip between us. I can't quite tell if it's up right now, right? And so then 3 is checked by 2 and 4. 3 responds. 4 says, yeah, it's totally still up. Everything's cool. And then, of course, you have the example of a down server where we do the same thing. 3 never responds. And we know that it's dead. Right? So that's like, it's actually a really simple protocol. It's hard to get like all the little fiddly bits of it totally correct. So I wouldn't recommend actually just going out and trying to implement Swim if you're actually trying to make a production system. Instead, you can use something like Memberlist. So Memberlist is a HashiCorp project. The whole idea here is that it's just a way of determining what is in it, like which servers are still alive at any one particular moment. That's the whole idea behind failure detectors. Failure detectors are actually like a totally fascinating area of distributed systems, which I totally recommend reading about, but we probably don't have time to go into it right now. So for our example system here, we're just going to use Memberlist. Great. That gives us an easy way to like achieve this fault detection thing that we need to achieve. Okay. So we have a way of load balancing using Rendezvous Hashing. We have a way of determining ownership also using Rendezvous Hashing. We'll use Swim via Memberlist for failure detection and cluster management. But of course, we also need a way to communicate. Everyone here is probably at least a little familiar with the concept of gossip, right? Periodically, each server decides to send messages that it has that is received from other servers or that it has generated itself, and it chooses other servers at random within the network and says, hey, here's what I know, or possibly it says, hey, what do you know? Please tell me things. So this is kind of the idea behind like push versus pull in gossip. Another way of doing gossip is that pull system, where instead of saying like, here's my messages, like a fire and forget type of thing, instead what you do is say, hey, what do you have? Please tell me things. There's advantages and disadvantages to both. So push, as you might expect, like if you're pushing, you know that you're immediately getting your messages out. And so when you look at like the growth rate of message delivery and a push-based gossip system, what you see is a huge spike at the beginning, and then it slowly levels out until it gets to every server in the network. Pull, on the other hand, is a totally different beast. What pull does is instead of saying like, here, fire and forget, you're waiting for someone to ask you about your messages, right? And so if you look at the growth rate of a pull-based gossip system, what you end up seeing is that for a little while, your message doesn't get around to anybody. And then eventually someone asks you. And suddenly, as soon as it starts to grow rapidly and hits every server really quickly. So it ends up being this like, they're both log n time, but they get there in a slightly different way. So in our particular case, for this particular application, we're going to go with a pull-based system. And I will try to explain why as we get into like a later part of the talk. But for now, just know we're going to go with gossip. It's going to be a pull-based system. Okay. So yes, convergence. Okay. So again, we're making an eventually consistent system. We're going to use rendezvous hashing for it, for load balancing and ownership. We're going to use Swim for failure detection. We're going to use some form of gossip for communication. And so that's actually much of the infrastructure of our system, right? That's actually a lot of like the actual like core guts of it. Like gossip, failure detection, okay, great. But we still need to talk about how we keep everything in sync, how we know that the system will converge in some way. I guess essentially what we're talking about is we need to design the protocol, right? So, okay, so let's talk about convergence. Like this is the idea of like knowing that regardless of like which way the messages arrive, when they arrive, like who is up and who is down, that eventually the system, every node will converge to the same set of values. Okay, so how do we do that? So going back to like the eventual consistency decision that we made early on, we can actually do better than just a like basic weak eventual consistency. Rather than, again, so going back to like linearizability and like one of those CP type systems, which assign a total order to events. Total order meaning essentially that like anything that happens in a CP system, you know that like this event happened before or after any other event. There's no non-determinism in there. So with causality, the idea is that we assign a partial order to events. So what does that mean? It allows us to say that some events happened before or happened after other events, but it also allows us to say that some events actually just happened at the same time. So one could think of it as like much more consistent with how the world actually works, right? Like our universe is a lot more causally consistent than it is like linearizable. So let's look at an example of this. Let's say we have two actors here. We have Jack and we have Jill. Great. So Jack and Jill are just trying to decide what they're going to eat for lunch. Jack suggests, let's have arugula. Great. Jack then says, okay, arugula. Tells Jill, I have decided upon arugula. Jill, on the other hand, is like, you know what? I don't like arugula. I like burgers. Jill wants burgers. And so what happens is, in this case, we know that arugula happened before burgers. So essentially this is going, okay, when Jill made the decision, burgers, she already knew that Jack had said arugula. Great. So we know that the burgers event happened before, or I'm sorry, the arugula event happened before the burgers event. So Jill then replicates that back to Jack. And Jack is like, no, I don't think so. I don't want burgers. I instead want calzone. Great. Well, while at the same time, Jill is like, actually, I changed my mind. I don't want burgers. I actually want dal. Okay, great. So in this case, what we can say is that burgers happened before calzone, and burgers also happened before dal. However, as we replicate those messages back and forth to each other, we now realize that calzone didn't happen before dal, and dal didn't happen before calzone. They are, in fact, concurrent with each other. And so that is the example of lunch-based causality. Okay, so now that we have like some basis for like what we're talking about with causality, let's talk about something that's related. Let's talk about lattices. So lattices, data structure, a mathematical concept of some kind. And specifically in this case, what we're talking about, if you wanted to look this up later or read about it more, is what's called a joined semilattice. So what that means is essentially it's a data structure, a concept of some kind, upon which you can always apply what's called a least upper bound, aka a join, aka a merge function, right? So what it's saying is that if you have two lattices, two joined semilattices, there is always a merge function that you can apply to them. Okay, let's talk about what that means. So lattices start from a root or a bottom value, despite the fact that our dot is at the top here. And from that empty value, if you're like operating on this thing, if you have three different actors that are operating on this lattice, they can diverge, right? But the thing is, those branches, no matter how much they diverge, can always be merged back together in some way. Again, no matter how much time has passed, they can always be like brought back together. At least two of them can always be merged. So, and then of course they can diverge again after that. Okay, so let's go back to causality. Turns out lattices are super useful for modeling causality for reasons that you can probably already see. And specifically in this case, what we're talking about is a concept called version vectors. The idea behind version vectors, well, actually, let's just walk through an example of a version vector scenario. Okay, so in this case, let's say we have three servers. We have S1, we have S2, and we have S3, right? S1 has an event of some kind. In this case, maybe it's doing a health check, for instance. Okay, so S1 increments its individual index in that version vector. So we have three nodes, we have three indexes, we have three slots in our version vector. S1 is going to increment 1 because an event happened, right? S1 can then replicate that down to S2, and now S2 sees, okay, I have seen S1's event. And from there, we can then go, okay, well, we have more events that are occurring, right? So in this case, S2 has its own event, and so now its version vector is 1, 1, 0, because it has seen S1's event and also has its own event. Meanwhile, S3 at the bottom hasn't seen any of these, so it is just incrementing its own. Then, of course, we can merge these back together from S3 to S2, and now S2 knows that it has seen the events from every other node. So that's the whole idea behind version vectors, right? So this gives us a way of tracking causality. It gives us a way of seeing, like, this thing happened before this other thing. So in this particular case, given that S3 hadn't actually seen any of the other events that occurred on the other parts of the system, its event is concurrent with all of the other ones. And you can determine that based on that version vector. And so, of course, it continues on. And so it turns out that you can actually model this exactly the way that you model lattices. So again, if you have your root value there at the bottom, 0, 0, 0 for our version vector, it can diverge, it can merge, and it can continue merging there, and then of course diverge again. Is this making sense? Cool. So one way of applying lattices to distributed systems problems is through this idea of CRDTs. And so what we're going to design next is actually what's called a coordination-free distributed map. It's a CRDT map of some kind. Okay, so we need a data structure that we can replicate, that it respects causality in our case, and is guaranteed to always converge. So again, CRDT map, great. Okay, what it looks like is something like this. And this goes back to like what we were talking about before with our pool-based gossip system. So what we're going to do is say, okay, when one node wants to exchange state with another node, it wakes up and it gets its own version. It looks at its own version vector, and it says, hey, here's what I have seen. This is my summary of the causal context I have seen so far in our distributed system. And it's going to take its version vector, it serializes it, and it sends it out over the network. In my prototype of this system, it actually just used HTTP. It could use really anything, any way that you want to communicate between them. So what it does is it sends this version, and it gives a way of summarizing. It says like, okay, I have seen up to this particular cut in our causal time. So what that does is it allows the node that it's communicating with to come up with a delta. That node also has its own set of like operations that it's seen. Like these two nodes are operating independently. One sends its version. This one can then take that version and go, okay, I know that you have seen all these things. Let me show you everything that's newer that I have seen. Great. So it constructs its delta, it sends it back, and then the first node can just merge it. Because again, this delta that we're operating on is actually a lattice. So it can always be merged back together with whatever state that node has. Pretty cool. So this is again called a delta. Oh yes, this is actually not just a regular CRDT map. What we're talking about in this case is a delta CRDT map. Because it's not exchanging the entire state each time, it's actually exchanging deltas, which are themselves a lattice. Okay, so let's just look at code. It's actually like surprisingly easy to do this. So this particular project was written in Go. So what we're talking about in this case is actually just a very simple thing. So we have our shared map at the top that we're going to exchange back and forth with each other. That shared map has its like actual underlying storage, and it actually has a version vector that goes along with it. So it remembers what its current state looks like, a summary of its current state. Each of the shared map records includes its value, but it also includes what's called a version vector dot. So where a version vector includes is a way of summarizing the entire state, a version vector dot is a way of saying this is one particular event. So a version vector dot in this case is actually just a tuple of a server ID and an event number, right? So it doesn't give you the full causal context, but it tells you where in that causal context this one particular value came from. Okay. So again, what we're going to do is for our delta CRDT map, the first step is easy. We just take our version vector, we serialize it, we send it over the wire. Great. Now, when our chosen gossip partner receives that particular message, what it will do is it goes through each record in the map, and it says, okay, did this version vector happen before this particular event? Which, based on the fact that you have this version vector that contains a summary of every possible event that occurred in the past, and you have the individual event that this value came from, we have a really easy way of saying, okay, did this event happen later? Or did it happen concurrently with it? If either of those are true, we know that that other node didn't actually see this event yet. So it gives us a way of deciding which things to put into our delta. Great. So yes, if the version happened before our individual record or is concurrent with it, we add it to the delta. Great, that's it. That's actually all we do. Then we send the delta back. And then the merge function here is actually slightly more complicated, but really not that bad. The idea here is that we go through each record in the delta And if the dot associated with the record still happened before our version vector, because again, remember, like when we're talking about sending things over the network, the state on each node may have changed since we actually sent the message, right? So now we need to go through and go like, okay, maybe we actually already got this message. So cool. We're going to go through each record in the delta, see if it happened before our version. If it did, then we skip it because we know we already got that, or we saw something later than it. And then we check and see like, oh, okay, was our version of this value older? If it was older, great, we merge it. All right. But then of course we need some way of determining what to do if they're concurrent, right? Because causality doesn't give us a total order, it gives us a partial order. So we haven't actually solved the problem of how to merge these records together if they conflict with each other. So what is that little sparkle that we're going to use there? This actually brings us straight back to rendezvous hashing. So rendezvous hashing gives us that way of breaking a tie in this case. There's many ways to break ties in like delta CRDTs or CRDTs in general, but in this particular case, for this particular application, rendezvous hashing actually ends up being perfect for us. It's actually probably my like favorite part of this little system, is that not only does rendezvous hashing let us decide on ownership for a particular origin server or a piece of work, it also lets us break ties deterministically. So when a node sees that its own operation has been usurped by some other node, it knows, oh, I should probably stop doing work on this particular origin server because someone else is a higher priority than me and they've already done the work for it. So it lets us not only determine tie breaking, but also deterministically determine ownership of a particular thing, which is pretty cool. So again, what we have now designed, we have built a delta state CRDT map. It was easier than we probably expected it to be. It's coordination free, but it's guaranteed to always converge to a deterministic state. So like no matter what order these messages are delivered in, no matter how long a node has been like out of sync, it will always, when it gets the messages, come back to the exact same state as any node in the rest of the system, which is pretty cool. So that's all actually based on this paper, which is actually a really short, really like digestible paper, based out of like the one of the Portuguese universities that's been doing fantastic work on this. And in that paper, you can actually see this like directly, right? We receive a version vector, we generate a delta. When we receive a delta, we merge it, and we periodically randomly pool. In other words, gossip, right? So this is a great example as well. Like I like the system, but it's also like a beautiful example of applying academic research to a problem, right? This is like, it's just one-to-one mapping basically. Okay, so at the end of this, like we've actually achieved all the goals that we wanted to in this particular little system without applying a CP system, without applying any linearizability. The system is entirely causally consistent, and every node can still always make forward progress. Great. Okay. So we've used rendezvous hashing, we've used swim, we have a causally ordered pool-based gossip communication system, and we're using CRDTs. So a great question that one might wonder is, why is a CTO of a company that is primarily known for content delivery up here talking about this? Why do I care about this? One thing I actually do care about is this concept of edge computing. The reason I care about this is because it's a lot, like we could do so much more in like widely distributed edge-based scenarios than we do today. Another way of like describing like edge computing, which is like a very marketing word, is actually just saying coordination-free distributed systems. If you're talking about an edge compute distributed system, really what you're saying is that I have a whole bunch of nodes and I can't keep them in sync at all times. I can't do a CP-based edge computing system. It doesn't make any sense. So it turns out that like all of the research that has been going on for decades in coordination-free distributed systems applies directly to edge computing scenarios. So why hasn't this like caught on more? Why aren't we doing more of these like crazy, like not fully consistent but still achieving the user's goals distributed systems? Obviously they're harder, sure. But I would argue that one of the things that holds us back is the prevalence of this idea in developers' minds: single system image. Single system image is basically an abstraction. It says that in a distributed system, regardless of the number of nodes that we're running it on, regardless of where they are around the world, we should provide an interface to our users that appears to be one system. You see this in like distributed databases all the time. The idea is that they want to hide the fact that it's actually running across hundreds of nodes from you, and instead like appear to just be like one individual computer. Another way of describing single system image is essentially to say that the system is linearizable, meaning that to an outside observer, it appears that that every single event has a specific order. For any two events, you can definitively say that one of them happened before the other. But as we were talking about earlier, that's not really how like the world and the universe actually work. Causal consistency is actually like a far more like accurate way of looking at how things happen in the real world. But it is sometimes trickier, and that's not the way we think about things necessarily as we're designing systems. I think it's our attempts at applying the single system image idea that actually like leads us to bad, hacky, failure-prone distributed systems designs. And so when it comes to like edge computing, this idea of single system image just straight up doesn't work. You can't do that. It's not realistic to hide the fact that your program is actually running across many, many nodes all simultaneously. So as I was preparing this talk, I was reminded that a friend had actually written an article specifically about this. It's called A Certain Tendency of the Database Community, which is like the shadiest title I have ever seen in a talk. So what we've walked through today is like, God, okay, actually. So what he says here is that we posit that striving for distributed systems that provide single system image semantics is fundamentally flawed and at odds with how systems operate in the real world. So what we've walked through today is an example of like an entirely coordination-free distributed system that still maintains the requirements and the invariants that we set out to achieve early on, without having to use strong consistency, linearizability, or single system image. So ultimately, what I'm saying here is that like this stuff isn't as hard as we often believe it to be. It is still hard and it's tricky, and like if you get it wrong, it's really hard to debug. But like what we need here, we need new metaphors because we have the single system image idea. Like that's a great metaphor for a certain type of distributed system. We don't have one for these types of systems that I'm talking about today. There is no easy way to say, this is what I like am imagining the system is going to do. We need new metaphors. We need new intuition for these types of things, right? We've all been building systems for a long time using this idea of single system image. And what we're lacking is the intuition to build systems like this. We also need more tools and frameworks for this. So that's all I got for you. Thank you.